Hello, welcome everybody in the 9th chapter of the Crystal Clear Electronics videos.
In the first video of chapter 9, we learned about the main parts of microcontrollers and revealed their similarities with computers used in everyday life. In this video, we'll take a closer look at the ATmega16A microcontroller. I'm Ambrus Zelei, and my partner will be Péter Buzás.
Thank you. Ambrus, there is a frog in front of you. Why did you bring it here?
We see microcontrollers in many places because us humans want to control almost everything around us. One of the tools to do this is the microcontroller. But it's interesting to see that we can also control things mechanically using a mechanism. This frog can actually sense that its feet are on the ground. This causes a sudden change in the flexibility of the leg, which makes the frog to jump up. So if I pull up a little bit and push the leg back in, then I can see with my fingertip that it clicks and exerts a much greater force. So there's a mechanical way of getting it to kick off at the right time. If it kicked away earlier or later, it would tip over. Let me show you how this works. And while we're on the topic, let's also say that when us humans walk or run, something similar happens. We feel our feet landing, we sense our body position, and at the right moment we start the next step. And this issue is related to the fact that in the case of a robot with 2 or more legs, this control could even be done by a microcontroller.
Before going into the details of the ATmega16A microcontroller, I suggest that we look at the microcontroller's areas of applications.
I agree. We could meet microcontrollers in almost every place if they wouldn't be hidden deep in our devices. Microcontrollers or very similar devices implement operation controlling and regulating tasks in most devices around us that have electronic automation. Today, almost every electronic device with buttons or even a display contains at least one or more microcontrollers. When we press buttons, a microcontroller in the background interprets these button presses and controls the operation of our device.
A háttérben egy mikrovezérlő értelmezi ezeket a gombnyomásokat, és ő irányítja az eszközünknek a működését.
Can you give us some examples? I don't think that we can use microcontrollers in too many places.
We use them all over the place. For example, the microwave or the washing machine both contain microcontrollers.
Do we use them anywhere beside the microwave and the washing machine?
If we stay at the household topic, I could say the dishwasher.
And if we think outside of the kitchen, where can we use more microcontrollers?
If you want to go to the streets by using an elevator, the elevator also contains microcontrollers behind the buttons.
And if we got out of the whole building, where can we find them?
Let's say you're headed somewhere, but you're hungry and you stop at a shop. There, you'll meet microcontrollers built into the credit card terminal, and when they scan your barcode at the counter, the device has them too. I can also add whole topics such as the automotive industry. There are lots of microcontrollers in a car, for example the wipers, the airbag, the window lifter, the mirror moving electronics. The ABS is a very important part of the car, and there are microcontrollers in that also. And the air conditioning is also controlled by a microcontroller.
Well, Ambrus, according to this, our life is filled with microcontrollers.
Yes, and we haven't even talked about your phone or TV remote. I'd say that the list is infinite. The microcontrollers are truly everywhere. I don't know if you are convinced now or not.
Oh yes, you convinced me.
Now that we've seen how many places microcontrollers are used, let's look at a specific example from the automotive industry. We've brought with us this 3 PCBs, which is an electronics for battery management. So it does the management of the batteries. It's easy to recognize this because there's this part where you have the same circuit with diodes, transistors, repeating 12 times. The point is that I can see that there are 12 iterations. This indicates that there are 12 cells of battery management being done by this electronics. Then, interestingly, there is a break in the PCB. This is because the 12-cell battery is expected to operate at a voltage of 50 volts, and we don't want these 50 volts to be able to be transferred one by one to the other part of the battery, where there are more sensitive components. So this part is isolated from the 50 volt part by optical or other coupling ICs. And here we also see that a pretty massive current can flow through these connectors if the connection is soldered here. We will try to electrically isolate this part. Turning it around, we can see that this low current part is connected to the other side to a... What's your guess? What part could this be?
A processor?
Yes, it is a microprocessor. You also see two other many-legged ICs. These are actually battery management ICs, but it's really a microcontroller. It's much more complex and has much more legs than what we're going to deal with, but the principles are exactly the same. People who have mastered the basics can jump on a system like this.
And the others?
The other two panels are a bit more general-purpose control electronics. They can be used in the automotive industry, but also in other processes. The interesting thing about this one is that it has a relatively powerful microcontroller. The packaging is called BGA, which is designed so that you can put a lot of legs in a small space. You can solder a lot of connections to the panel. This little piece of electronics rivals the capability of virtually a tablet today, so it's a pretty serious system. However, I'd like to point out that there is another general-purpose control electronics, and the interesting thing is that there are two microcontrollers in this one. We've already said that there is not always one, but sometimes more. The interesting thing about the microcontrollers themselves is that they are the same as the ones you will learn to use in Crystal Clear Electronics 2. In conclusion, the reason that microcontrollers are so widely used is that they are programmable. If you want to use a particular microcontroller for something else, you simply load a different program onto it, and the microcontroller as the hardware remains. The ATmega16A microcontroller, which you will learn about in this tutorial, can also be used for a variety of tasks.
From what I've heard, there are a lot of microcontrollers being produced. Can you give me some details?
Yeah, starting from the 70s, it's been increasing every year. Nowadays, they produce several billions every year. But now, let's get to know the ATmega16A microcontroller. At first, what does it look like? It's integrated in a small black case. As I mentioned earlier, we're talking about an IC. On the website of the curriculum, under the Extra Materials section, you can download the datasheet of the ATmega16A that we will refer to. You will also find a reference to the manufacturer's website. You can find more information about the packaging, or packaging information, on pages 325 to 327. Out of these, we have also chosen the through-hole one to make it easy to use on a breadboard. Atmel marks this package with the code 40P6, which means that the component has a total of 40 pins, and the distance between the two lines of pins is 0.6 inches, or 15.24 millimeters. This aligns perfectly with a breadboard, where the distance between rows is 0.1 inches, or 2.54 millimeters. Usually, this package is called DIP40, which indicates a 40-pin component with two lines of pins on the casing. The DIP abbreviation means dual inline package.
So we have a nice compact component with lots of legs. Please tell us how we know which leg does what.
At first glance, all legs look the same, and you don't even need to know off the top of your head which one does what. That's what the so-called pinout or pin assignment shown here is for, and it can be found on the datasheet of every microcontroller and every IC in general. In this case, it's in the form of a diagram on page 3 of the datasheet. The datasheet can help you a lot to read the figure, and every pin's precise description can be found inside the overview under pin description section.
Amit pedig úgy mondunk angolul, hogy pin description.
Because we learn about every single function, one by one, now it isn't necessary to understand the operation of every single pin and the circuit that is behind them.
And what if we would only identify the legs that are needed for the power supply?
I agree. Since the microcontroller is an active component, it needs proper supply voltage for its operation, which we need to connect to its dedicated pins. Most microcontrollers, including this ATmega16A, have multiple power supply pins. For correct operation, we need to connect the appropriate voltage to every single power supply pin. The pins labeled G and D are the ground pins, the VCC and the AVCC are the supply pins. In every microcontroller's datasheet, they indicate the operational voltage range, which in our case can be found in the electrical characteristics section on page 281.
Electrical characteristics néven. Az ábra
The figure shows the safe operating area, which means our device will operate safely between 2.7 and 5.5 volts of supply voltage.
2,5 volt között fog helyesen működni. Az ábrán az is
You can see in the figure as well what clock frequencies can be used for different supply voltages.
órajel frekvenciát állíthatunk be.
The clock frequency is the same as for the processor in the PC or laptop. An Intel i5, for example, runs at 2.6 GHz by default. We have seen in the previous figure that the clock speed of a microcontroller is on the order of 1000 times slower than that.
Valóban az
Indeed,
vezérlőknél főleg a
but with microcontrollers, the goal is reliability and economy, so with a well-written program, you can do a lot at 8 MHz.
órán is nagyon sok mindent meg tudunk oldani. Tekintsük is át
Let's look at the main information about the operating speed.
információkat. Az órajel
We'll set the clock signal's frequency at the time of programming, and this will give the operating speed of the microcontroller.
frekvenségét. Nagyobb frekvenciát
Higher frequency means faster speed, which means faster operations, but the power consumption will increase by a little too.
cserébe. 8 megahertz
So, the 8 MHz frequency means that in 1 second, this device could complete 8 million additions.
8 millió összeadást tud elvégezni. Láthatjuk azt is,
We can also see from the datasheet that the clock frequency can be set to 16 MHz too. This is twice as fast, but at least 4.5 volts of power supply voltage is needed.
törekedni, ezért a tananyagban
For now, we are not aiming for low power consumption or very high speeds, so for simplicity's sake, we will use the 8 MHz internal oscillator, but give 5 volts of power supply to the microcontroller.
The power supply and the clock signal have strict maximum limits. What other limits should we look out for?
In every case, it's worth to examine what the maximum physical limits are, voltage, current, etc., for our device. These are not for operation, but they are the values that the device's supply pins, other pins, or casing can tolerate without damage.
adatok, amik
This information can be found on page 279 of the microcontroller's datasheet.
számunkra mindegyik
For us, every piece of data can be important later. At the time of installing a periphery, we'll have to look back here and use them for the calculations. Maximum operating voltage. If we connect a voltage bigger than 6 volts to the power supply, even for a short period of time, our microcontroller may be damaged permanently or become completely faulty.
maximum feszültség
Voltage on any pin. It's prohibited to connect the voltage to a single pin which is lower than minus 0.5 volts with respect to ground, or higher than the power supply, 5 volts in our case, by 0.5 volts.
5 voltnál többet. Maximum áram az egyes
Maximum current on each pin, DC current per I/O pin. A current bigger than 40 milliamps is not allowed to flow in either direction. Maximum current on supply pins, DC current VCC and ground pins. A current bigger than 200 milliamps is not allowed to flow on either power supply pins.
nem folyhat 200 milliampernél több, egyik táplában sem.
Now we recognize the pins for the power supply. What about the other legs that are not important for the power supply?
Most of the pins are used as a digital in and output.
Szolgál. A PA
All general purpose pins, such as the PA0 to 7, PB0 to 7, PC0 to 7, PD0 to 7, can be used as digital inputs or digital outputs.
digitális kimenetként is.
Notice that each of the 4 groups, this is A, B, C, D, have 8 pins corresponding exactly to 1 byte.
A digitális
A digital input can determine whether the connected voltage is a logic low or high value. We can get a logic low value if the connected voltage is 0 volts or a value near to 0 volts, and we can get a logic high value if the connected voltage is near to the power supply.
értéket pedig a távfeszültségnek a közelében kapunk.
Távfeszültség megjelölése.
The power supply voltage designation is VCC, and the voltage value is often set to 5 volts, which is the theoretical voltage value for logic 1. The 5 volts is of course slightly inaccurate. A digital output connects the logical low or logical high to the pin depending on what we previously set in the software or how we change the value on the output during operation.
In summary, the IC either observes what voltage is on a particular leg and then it is an input. The information flows into the IC from the outside.
Felé. A másik eset,
The other case is when it functions as an output, in which case the IC generates 0 volts or a voltage corresponding to logic 1 on the leg, and this is supplied to an external part, a periphery.
egy periféria számára biztosítja. A 9-es számú tananyag
We plan to get to this section in the second video of the 9th chapter. Try to master what you have heard thoroughly. Then feel free to move on to the third video.
tovább a harmadik videóra. Ez a témakörünk nagyon
This will be a very important video for our topic as we finally get our hands on our microcontroller. Peter, thank you for your help.
I want to thank you as well. See you in the next video. Bye bye.
Bye!